For the remainder of today's lecture, we're going to show that composition of these binary-ish mechanisms can be done in this advanced way. That, in fact, the advanced composition theorem holds for just these ones with 4 different possible outputs. So by the argument in the previous part of this lecture, that shows that overall that we have the advanced composition theorem. So okay, in particular, we're going to want to show the privacy loss random variable for the following sequences is bounded. The sequences will be U1 through UK versus V1 through VK. We want to show that the privacy loss random variable is less than or equal to, or an absolute value is less than or equal to epsilon with probability 1 minus delta. Rather, recall that the parameters as we define them, we were trying to prove advanced composition with parameters epsilon tilde and delta tilde, so these will be the 2 parameters we use here. So what are we going to do? We're going to prove the privacy loss random variable with U with respect to V as this bound in particular. So how do we do this? How do we prove this? Well, as usual, we're going to sample according to the former sequence. So in particular, we're going to let Z be a random variable in or this will be the realizations actually. It'll be in 0, 1, IMU to the K, and each the J will be sampled according to the distribution U. So that's sort of how we're going to use this as a notation as we kind of go through it. How is our analysis going to go? Well, we're going to break it up into a few different cases. We're going to try to we're trying to partition the different cases so that we can get rid of some bad events early and then deal with some nicer cases. In particular, that is a bit vague, but let's say, let's try to rule out some of these outcomes, some of these sequences of Z's, which are, say, blatantly, or not blatantly non-private, which are obviously unbounded. So remember that we're trying to say that the privacy loss random variable is bounded with high probability, but let's try to get rid of some events which make it obviously be unbounded. In particular, recall that if any of these ZJs is sampled and drawn and is realized as IMU, then in fact the privacy loss random variable would be infinite because of the fact that V assigns probability 0, so anything divided, like any non-zero divided by 0, is going to be infinite. So the first event we're going to define is the following one. So E1 is going to be the set of all Z such that there exists J such that ZJ is equal to IMU. So the idea is first we're going to try to partition out all of the events. We're going to sort of say that we're going to try to understand this event and we'll condition on its complement in the future. Because we just want to deal with nice bit strings, 0s and 1s, but these kind of mess up the analysis a bit. And in particular, this is very easy to understand. So why? The reason is because of the following. The probability of E1 is, we did this in the name and shame example in the last lecture, but I'm not going to walk through the calculations again this time. You can check the last lecture if you'd like. But the probability that at least one of them is output is the following quantity here, which, as we said, is sort of approximately equal to delta times K. So yeah, this is sort of like, let's recall, what the expressions are. This was going to delta, let me do it as follows. Delta tilde is equal to delta K plus delta prime, and epsilon tilde is equal to, how do we do this? This is like, let me do this from memory, epsilon square root 2k log 1 over delta prime. plus epsilon k times e to the epsilon minus 1 over e to the epsilon plus 1. So that's just a reminder, but like I'm going to just give you some intuition where these terms are coming from. This event E1 is going to be the one corresponding to this delta k right here. That's kind of the correspondence between these two terms. So we're kind of going to sort of factor this out in some way. I'm using that term informally. But then we're just going to be focusing on bounding the privacy loss by this with probability 1 minus delta prime when, you know, conditioning on the fact that epsilon 1 does not happen. So yeah, we're yeah, like I said, we're going to continue assuming we're going to condition on bar E1. But so what this means is that the z vector is going to be in 0, 1 to the k. Let's try to understand what the privacy loss random variable looks for any realization of, for any realization when z is in 0, 1 to the k. So let's suppose z is in 0, 1 to the k now. Well, what is the privacy loss random variable? Let's write it out explicitly one time here. It'll be natural log of following. The entire transcript is equal to the vector z divided by same, except v is in here. And this is equal to z. Okay, so that's the expression for the privacy loss of a random variable. Well, fortunately, this is very easy to simplify because, like I said, these are drawn IID from the same distribution. So what you can do is break this probability out into a product over, a product over U1 equals Z1, U2 equals Z2, and so on. So breaking up into a product is the first step. You can do the same thing for the denominator. And then you can break it up. You can pull the product out of the natural logarithm, which will overall make it a summation. So we get summation j equals 1 to k of ln times the probability of just a single one. So uj equals zj divided by the same thing for the vj. Okay, so that's the first step. We break it up into each sort of component. Now, this is actually fairly simple to understand. Why is that? Because we know exactly what these probabilities in the numerator and denominator are. They're a little bit of a mouthful, but I'll write them out nonetheless. So it's going to be summation of ln, where here we have the numerator. It'll be 1 minus delta 1. So, okay, what did we do here? We essentially just took the probabilities from this table and substituted them in. You know, if you match it up, the one thing that like the kind of clever trick is noting how we did this thing where you see here it's to the 1 minus zi. Well, if you set zi to be 0, then this would become e to the epsilon, which is here. And if zi is equal to 1, then this would simplify to 1, which is sort of the opposite case. So this is just like a cute little notational trick that we played in order to get it to match up here. Well, if we take this ratio, cancel the like terms, this will cancel with this will cancel with this, and so on. You combine these and you take the log to get things in the exponent down, and so on. I claim that, you can work this out and simplify. It'll give you something nice and simple like this. Where the summation is from j is equal to 1 to k. Okay, so this is the privacy loss random variable for any realization, for any sort of z in the set. Okay, so this is how it's distributed. So let's iPhone. So let's actually let's make a comment about this. We'll note that the privacy loss random variable is now in a very nice format. In the sense, why? This is the format of the privacy loss random variable, where in fact, if we condition on the event that none of these if we condition on E1 not happening, then in fact we have that this is a sum of independent random variables which are all bounded. Let's see this in particular. What we have is that zj is going to be distributed as u. So you can see that this is going to take one of two different values. So suppose zj is equal to 0, then this will take the value each term in the summation. Let's say we'll take either the value minus epsilon in the case when z is equal to 0, when z is equal to 1, or it's going to be epsilon in the case when z is equal to 0. So yeah, all this to say is that it's just going to be a sum of bounded random variables which are all independent. So those are all key terms which are very useful. It's going to be sum, they're going to be independent of each other, and they're bounded. And in fact, these are three properties which make it very convenient for us to use some of the concentration inequalities we've mentioned before. I'll write what it is in a second, but let's talk about the expectation of this random variable first. So essentially what we're going to try to do is say that the privacy loss random variable is small with high probability. So like we're going to do this using the same type of thing as we said before. We're going to compute its expectation and then use a tail bound to see how much bigger than its expectation it'll be. So let's see. What we're going to do now is we'll first compute the expectation of this, which is not too hard to see. In particular, recall that we're conditioning on epsilon 1, or bar of epsilon 1, meaning none of the zj's are IMU. So we're conditioning on bar of E1. And so we can write now the following expression for the expectation of the privacy loss random variable conditioning on this event. So the expectation, where z is drawn from u1 through k, yeah, they're just writing exactly the privacy loss random variable again, not too exciting. But the special thing is now, this time, like I said, we're conditioning on bar of E1. And in this case, I claim that this random variable is the expectation of this random variable is equal to k epsilon times this e to the epsilon minus 1 divided by e to the epsilon plus 1. Now, where did this come from? How did I get this term here? It comes from this expression here, but with a little bit more careful reasoning. In particular, what do we know about zj? Zj was supposed to be, like here, what did we know about zj? We knew that if we're just sampling from u, zj is going to be equal to 0 with probability e to the epsilon over 1 plus epsilon times 1 minus delta. However, here there's two differences. One, we're not just looking at what the value of z is. We're looking at the value of 1 minus 2z. Sorry, this should be e to the epsilon. Yeah, so one, we're looking at a transformation of the z. And the second thing is we are also going to be conditioning on the event E1 bar. So therefore, if you do the calculations perhaps using Bayes' rule, then you'll get, in fact, that this term just sort of disappears. Like if you condition on that delta probability event not happening, then it'll just be distributed as this. So in short, what we'll say is that 1 minus 2 times zj is going to be equal to 1 with probability e to the epsilon, e to the epsilon over 1 plus e to the epsilon, and equal to minus 1 with probability 1 over 1 plus e to the epsilon. And so all we're doing is, pushing this expectation through into this expression. Then we have here that the expectation is equal to k times epsilon times expectation of 1 minus 2 zj, which is equal, if you just work it out, the expectation here is equal to this, just using this calculation here. Good. Okay, so at this point, what have we done? We've calculated the expectation of the privacy loss random variable, and we'll note, let's note that this bears a significant resemblance to what we've already written above somewhere. So this is like k epsilon times this term here. Well, recall that this was exactly the latter term here. So what we've got is an expectation, and we're essentially going to show that this privacy loss random variable doesn't deviate more than this much away from its mean with probability delta prime. So maybe you can see now where these two things come from. We're going to, push this. If we push the tail bound further out, then there'll be a smaller probability, but we'll be left with a larger epsilon tilde as a result. Yeah, it's kind of like choosing the right point in the tail bound for how far out we want the probability to be. Okay, so yeah, at this point now, all we have to do is show this tail bound. What we're going to do is essentially do the same type of thing, just using, we're going to define another event, and we're going to analyze this using a tail bound for a Gaussian. So E2, I claim, will be the following set of strings, or the following event where U takes something from these strings. So this is going to be when, Z is something which is in 0, 1 to the k. So that, therefore, it's sort of like conditioning implicitly on E1 because there's no IMUs here. And this is where, okay, I'll just write this in shorthand. No, I guess I have to, I'll just write it as follows. There's the privacy loss random variable again. I just don't want to have to write the whole thing again. So let me just write this as U vector is equal to Z divided by the probability that V vector is equal to Z. So this is just the privacy loss random variable between U and V, the entire vectors. And this will say that the privacy loss random variable is greater than k epsilon times e to the epsilon minus 1 divided by e to the epsilon plus 1 plus t epsilon square root k. Okay, so this is essentially saying this is the event where the privacy loss random variable exceeds its expectation by this much. And this is going to be sort of specified in terms of the t is sort of a parameter which we're going to define a bit, but this will be kind of the tail bound that we're going to do. Okay, so what is the probability of E2? This is going to be the key sort of last piece that completes the proof. But what we're going to do is we're going to use the following type of Chernoff bound. It's a Chernoff-Hufting bound. Let me just state this bound. So suppose, I'll write on the, I guess we still have space on this page. So let me just say this is the Hufting bound. And what we're going to do is we're going to assume that we have Z1 through ZK, a capital this time. ZK are independent and bounded. That is, you know, each of them are in the range L comma U. So remember, independent, bounded, and we're going to have a sum. So this is like exactly the three things that I said we're going to hold. And these are going to be the useful properties we have. So I claim that the Hufting bound is the following tail bound, saying that the probability that you have the summation of the ZJs is greater than or equal to, you know, the expectation of its summation plus, say, some tau some additive tau is going to be less than or equal to the following: exp of minus 2 tau squared over the sort of range squared. And then there's a k here. Okay, so this is the Hufting bound. You can refer to some references, which I'll provide to see this, but this is the Hufting bound, and all we're going to do is we're going to essentially plug in, you know, what are we going to plug into this? We're going to plug in these summons here, because the privacy loss random variable can be expressed as a sum of these random variables. What else are we going to plug in? We're going to plug in the L and the U, because we know each of these summons is between minus epsilon and epsilon, and we're going to, in particular, plug in a very carefully chosen value of tau. In particular, tau is going to be this sort of very serendipitously chosen t times epsilon times root k. So a lot of you know, talk here, but let me just write essentially what the conclusion is. This will tell us if we do those things. Let's say, let me write them out. So set L comma U is equal to minus epsilon epsilon. We set tau is equal to t times epsilon times square root k. And then we're going to get the following. And we're going to let these ZJs, or capital ZJs, sorry, bad notation, but they're going to be these things here. So the probability that you know, this term right here, it's essentially going to be this exact thing here. Let's say the probability that ln probability of the u vector is equal to z divided by v vector being equal to z. This is greater than its expectation, so we want the expectation of the term, and we know what that is. We've already calculated it. A epsilon times e to the epsilon minus 1 over e to the epsilon plus 1. And then we're going to set, like I said, tau to be plus t epsilon square root k. And just plugging this all in here, this is going to be less than or equal to exp of, well, let's just write it out, to t epsilon square root k squared over k times u minus l. So this is going to be 2 epsilon squared. And this is equal to, let's just, you know, if you work it out, this sort of a 2 and a 4. So this becomes a 2 in the denominator, 2 epsilon squareds cancel. And then also these root k's cancel. And then this just becomes t squared over 2. So, okay, let me, this is like a lot of math here, but let me just rewrite this event here as saying that probability of E2, conditioned, however, on E1 not happening, is going to be less than or equal to exp of, sorry, there's a minus here, minus t squared over 2. So now at this point, you can see kind of we have all the pieces in some vague sense. Like what I mean by that, you'll note that, you know, we have these terms. We already discussed about this delta k here, and we discussed about this you know, term here, which is the expectation. And you can see here that we have epsilon root k and this t. This t is going to kind of be the square root 2 log 1 over delta prime, and delta prime is going to show up as this bound here. But like we kind of have all the pieces, my claim is. We just have to put them together in a rigorous way. Yeah, let me try to tell you the story about this random variable, the privacy loss random variable. We can say, okay, first of all, it's going to be, blatantly or obviously, having a large privacy loss random variable with probability, delta times k if one of them is equal to u. But then what we can say besides that is that the privacy loss random variable is going to be fairly close to what its expectation is, except with some tail bound, which happens with probability delta prime, which we quantify here. So that's the story in words. Let's see how we would translate that to equations. This might be a little bit opaque, but you can you can verify that this is kind of corresponds to all these different parts in the story I just told you. So let's let any outcome. We'll do it as follows. For the first thing we're going to show is that probability that u is equal to some like vector z, and you don't have e1 and you don't have e2. So this is kind of saying that what is the probability that you have something in you have a set of outcomes for the like random choices of the z's from u, such that first of all none of them say I am u, and also it's not too much bigger than its expectation. So we can say the probability of any of those events, because the privacy loss random variable is bounded in this case, is upper bounded by e to the epsilon tilde. That's basically what this says, times the probability of v is equal to z, and not e1 and not e2. And this can always be upper bounded by, the probability that a and b and c happen is less than the probability that just a happens, because the conjunction, you're kind of wanting multiple events to happen. It's always more likely for fewer events to happen. So this is an upper bound that we have. And now let's take into account all the other things going on. So let's sort of complete the proof with the following thing. So let's do it as follows. So the probability, this was sort of conditioning on these two events, but let's do it for a general z. So the probability that u is equal to z, well, we'll partition this in a kind of weird way. We're going to separate it into its conjunctions, or into like the intersections with different probability events. So first is going to be the same thing we had before. Plus this. Plus this. Okay, now this might seem a bit arcane. We kind of took the intersection with, 3 different events. Why is this the right thing to do, or why is this like even true? Why is this an equality? Well, it's the rule of the law. Sorry, this is called the law of total probability. If you just sort of look it up, this is the exact same thing, but essentially says that if you take, if you sort of take the intersection with a set of events which partition the space, then it'll be equal. So it might not be clear that these actually partition the space. I had to double check this myself, but let's see that, if you have E1 and E2 as events, then this sort of split breaks up the space, partition the space. So like we'll draw this as a little type of Venn diagram. So, in this little space, we'll have everything corresponding to E1. In this space, we have everything corresponding to E2. This space in the middle is E1 and E2, and this is, bar E1 and bar E2. So, let's just verify that these terms correspond to the terms there. So this is like this term here where we have, bar E1, bar E2. That's this term over here. That's this space partition. This part of the space over here. The second term, where we take the intersection with E1, well, this is going to be this space here. That is the whole space, including the intersection. And the final term here, which is where we do E1 bar intersect E2, well, that's exactly, this space. So you can sort of confirm that there's a correspondence between these terms and all the space in the Venn diagram. So it kind of shows that this set of three things is indeed a partition of the space. This was like a little bit mathematical, but it turns out you sometimes have to get a little bit technical when trying to work out how to partition the space properly. Or you're kind of pushing around symbols here, but trust me when I say that this corresponds to like real events and kind of the story I told you. And let's sort of unpack this in piece by piece. So the green term, let's bound the green term first. Well, that we can actually bound, using what we derived in the previous line. We said that this is upper bounded by, I'll write it in green now, e to the epsilon tilde, probability that v is equal to z. Next, the blue term, well, what is this? This can be upper bounded by just say probability of E1 bar. And this is the same reason as before, if it's A and B, that's less than the probability of just B happening. And similarly, the third term can be written in the same way, like get rid of this U equals Z, and then also split it up using, I guess, just basic probability facts. So we'll do this, probability of E2, conditioning on E1, times probability bar E1. So that's how we'll break it up. And yeah, then we can upper bound this as, just by plugging in all the expressions we have. So again, this is e to the epsilon tilde, probability that e is equal to z. This term here is going to be plus delta, because we remember the probability of, delta k. We said that the probability of E1 bar is going to be, sorry, I made a mistake here. This should be probability of just E1, not E1 bar. And yeah, that's upper bounded by delta k. We showed that before. And then finally, the last term here is just going to be upper bounded by, we computed this right here, exp of minus t squared over 2 times, this can be upper bounded by just 1. And the final step in this whole sequence, in the whole proof, will be just to set t is equal to square root of 2 log 1 over delta prime. And if you do that, then you'll see that this will overall give you, this is less than or equal to e to the epsilon tilde, probability that v is equal to z, plus delta k plus delta prime, where this is overall equal to delta tilde. And that's exactly what we wanted. Recall that, now we've shown that the privacy loss random variable, or this is exactly the epsilon delta definition, right? You see that the probability of this event is less than or equal to the probability of this event, plus, this term right here. And so that completes the proof. So now we have this very nice theorem, the advanced composition theorem, which is sort of one of the very useful facts about approximate differential privacy in comparison to pure differential privacy.